Good morning, everybody. I am Mirko Piersanti from the INFN University of Rome Tor Vergata. This talk is focused on the definition of both the instrumental and environmental backgrounds in the electromagnetic emissions above seismic regions, developed for the newborn CSES satellite. Despite many ionospheric lithospheric coupling observation, the physical mechanisms regulating the electromagnetic emissions during a seismic event are almost unknown. In particular, just the generation of electromagnetic emissions during the preparation of an earthquake. So, we need a way to discriminate in the ionospheric observation the effect caused by natural sources such as the sun and the troposphere from what is caused by seismic sources. A first tentative to fix this problem was done by Nemec et al. In 2008 using Demeter data. They built an environmental background map over a grid dataset in order to have the statistical significance of the results that they use as a reference in order to identify possible ionospheric magnenospheric disturbances, possibly related to a seismic event. Their algorithm is based on two items. First, they create a statistical map of the intensity of electromagnetic emissions using the entire Demeter data. Then they estimate the probability of electromagnetic emission occurrence during an earthquake using the map as a reference threshold for the intensity. But this approach has two problems. First of all, no link to and no reference to external drivers is supported in their approach, such as the sun. In addition, they start from the effects and not from the possible causes, such as thunderstorm, ionospheric bubbles, sun eruptions, and so on. What we propose here is a new way to evaluate the background, electromagnetic background map via the use of a new data analysis technique that is called ALIF, that is able to identify and quantify variation at different scales for nonlinear and non-stationary signals through a time-frequency analysis. This method is similar to the empirical mode decomposition, but differently from EMD as a complete mathematical theory, assuring an a priori convergence and stability of the method. The key idea behind this method is the divide et impera approach, which allows overcoming the limitation in the time-frequency representation. ALIF first decomposes a signal into several intrinsic mode components. An IMC oscillates around zero, but not necessarily with constant frequencies. Then ALIF performs a time analysis on each component separately. This kind of approach allows eliminating the problems due to both the uncertainty principle and the interferences. To study the physical meaning of each IMC and connect them to the scales that in our case is frequencies associated to instrumental noise, we first use a statistical test, the standardized mean test, that helped us to sum back the IMC. Then we made a multi-scale statistical analysis. That means that we have evaluated the mean momenta of each probability density function for each IMC. The basic idea of the standardized mean test is if a clear time-scale separation exists in a dataset, this can be divided into two different contributions. That is, a baseline S0 and variation around the baseline, that is delta S. The idea is that delta S has the following characteristics as a close to zero standardized mean and represents the fluctuating oscillatory contribution to the time series. Using the local orthogonality and completeness properties of Aleph, we define the fluctuation delta ST as the reconstruction of a subset of the first k empirical modes which satisfy the previous two properties, where k in this formula is the last IMC for which delta ST has a standardized mean equal to 0. For each IMC, as I stated before, we made a multi-scale statistical analysis. That means that first of all, we evaluated the probability density function for each IMC. Then we evaluated the excess of kurtosis, the relative energy, and the Shannon information. How we define the instrumental noise? Just starting from the statistical properties of each IMC that we derive from the multi-scale statistical analysis. Since we know that the excess of kurtosis indicates how the different scalar reach of ray fluctuation, and since the Shannon entropy measure the degree of randomness of each IMC component of the signal for each frequency, we can define the instrumental noise as the subset delta S1 that satisfies at the same time the following two properties. First of all, the excess of kurtosis is around 0. That means that is a Gaussian fluctuation. And the Shannon information presents a relative maximum. How we define the environmental background? We divide the planisphere into 1:1 latitudinal longitudinal cells. We evaluated the relative energy for each cell in the following way. The entire dataset is divided into 6 subintervals depending on the geomagnetic activity and on the local time of the satellite. This is to take into account possible external sources different from the seismic one. Each cell is decomposed by Aleph, and the relative energy is evaluated. For each cell and for each scale, we evaluated the ratio between the relative energy for each orbit and the average relative energy evaluated for the entire dataset. If the ratio is greater than 1 plus or minus 3 sigma, then the relative energy of that orbit is inserted in the evaluation of the average, else it is defined anomalous. So, in this case, we have a map of the average relative energy that is a function of the frequency and the time that we define as the environmental background. Let's see a case event. Here we show the electric field trace observed by the CSES satellite. The instrument of the electric field is the electric field detector on the 4th of August 2018 over L'Aquila geographic position, that is a city, a town in the middle of Italy. In this case, we are using the geographic reference frame. This is the result of the map of the relative energy, the background map of the relative environmental background map of the relative energy over L'Aquila for the 3 components of the electric field. A clear signature of the first Schumann ionospheric resonance detected at excess orbit is well defined and well highlighted by the print circle. The peak detected at 2 Hz is due to the V cross P electric field present in the ELF band, and the peak around 1 kHz is the signal of the plasmaspheric ease. This is another example of the environmental background detected at very low latitude in Indonesia. Also in this case, a signature of the first Schumann ionospheric resonance is detected at all the 3 components. Also in this case, we have a peak due to the V cross B electric field, and also in this case, we have a peak around 1 kHz that is representative of the signature of the plasmaspheric ease. But in this case, we have also a peak that is typical in this region, around 250 and 300 Hz, that is a portion of the Whistler mode cause generated around health shell equal to 5 that propagates into the plasma sphere. The same can be repeated for the search-called magnetometer. In this case, the first Schumann ionospheric resonance is not visible since the search coil instrument have a band that starts from 15 Hz, but there is a clear signature of the second Schumann ionospheric resonance at 20 Hz. Also in this case, we are over the Indonesia. The peak around 12 kHz is the signature of the lower hybrid resonance of ionospheric F2 layer. Let's see now an example of anomalous peak that has been detected soon after an earthquake over in Indonesia. This is the electric background, and this is the anomalous spectra. An anomalous peak at 180 Hz along Y and Z component, and at 630 Hz along the only Y component, has been detected with respect to the background, magenta lines and red lines. The same has been detected for the search coil magnetometer for the same day and the same orbit, with the same frequency of 180 Hz along BX and BZ component. Interestingly, this oscillation is perpendicular to the one detected to the EFD, so we are confident that it is an electromagnetic wave. To conclude, the correct identification of a background in electromagnetic emissions during or before an earthquake as a crucial rule for the detection of possible signals related to earthquake or pre-earthquake activity. The algorithm represented here represents a new and very efficient technique to discriminate among instrumental, environmental, and external source signals from satellite observation. Our method was able to determine all the noise frequencies declared in the electric and magnetic field experiment of the CSCS satellite. We present a useful method for the correct selection also of anomalous signals with respect to the evaluated background. The choice of using a ratio was to take into account possible anomalous energy enhancement as well as new signal onset. We use a 3 sigma in order to make a selection as strong as possible to exclude possible positive false. Finally, the external origin perturbation in terms of solar activity represent the principal disturbance of both the Earth's ionospheric and electromagnetic fields. So this kind of approach that takes into account exactly possible external source represents a very good and useful method. Thank you very much.